We're live.
Ladies and gentlemen, tech enthusiasts and cable aficionados, welcome back to another exciting episode of Get Your Tech On. I'm your host, Brady Volpe, founder of the Volpe Firm and Chief Product Officer of OpenVault. And today, our show is a focus on DOCSIS 4.0. It's here. Should you stay or should you go? Back again for episode 94 is John the Cable Cruncher Downey. He says he's retired, but we know he's always wired. Welcome back, John.
It's always good to be back. Yeah, I would have came up on 23 years at Cisco this month, and I opted to take the exit package. So I took the package from Cisco, and I'm going to do some consulting on the side for Technetics. They have some cool RF stuff, which is right in my wheelhouse, for the last 30 years. So it's been a good ride, but RF is not dead, obviously, right? I mean, there's a lot more runway to go.
Yeah, we got a long future on it. So, well, that's awesome, John. That's exciting news for you. I think the consulting world is an exciting world. Obviously, I've been doing it for a long time. So, so I think we got some cool stuff to talk about today on DOCSIS 4.0, DOCSIS 3.1. We were at the Cable Tech Expo a couple weeks ago. We saw the latest technology, so I think that kind of blends well into what we'll be talking about today with 4.0 and the technologies related to that. I think one of the things we'll talk about kind of at the end is if you're a cable operator and you're on 3.1, it's like how much more can we get out of 3.1? Should we be even looking at 4.0? And kind of where we're going there. So folks, if you're watching, please drop your questions in the chat. We'll be sure to answer those questions, and smash that like button. And if you haven't already, please do subscribe so you get notified when we launch our next video. So with that, John, I think let's start talking about I think we should just dive in, like, why are we even doing DOCSIS 4.0, the differences between FDX and Extended Spectrum, ESD Extended Spectrum DOCSIS. So the first off, why DOCSIS 4.0? What's it at? What are your thoughts on that?
So we know what we got with DOCSIS 3.1, and it extended our upstream spectrum to 204, which allowed us to get more spectrum utilization and more OFDMA, DOCSIS 3.1. And we know what we can get out of that.
Well, what is that? I mean, 3.1, we
could offer a 1 gig offering.
Yeah, that's been a goal. 1 gig in the downstream.
That's like our panacea, our holy grail. Like, that's what we're going for, right? To be able to offer 1 gig symmetrical. It doesn't have to be symmetrical, but to be able to say you can offer 1 gig on the upstream is huge.
But to do 1 gig on the upstream, you have to expand. You can't have a 42 megahertz return, right? You have to extend that.
Yeah. The best you can get out of 42 megahertz, we said, is probably realistically like 100 meg service. Right. And that's pretty good, right? 100 meg offering. And that's over subscription and, selling it to a lot of people.
Correct.
The aggregate, when we looked at OFDMA mixed with single carrier QAM with a 42 megahertz system, you can get about maybe 150 megabit per second aggregate. So offering a 100 meg service is realistic.
Yeah.
But the more people that sign up, the more we're hurting each other.
We got to expand our 42 megahertz return to an 85 megahertz return.
Yeah. So
what can we get there?
Split, a mid split, and now the high split is 204, right?
Right.
So that's kind of the terminology people have been using, is the sub split's 42. In Europe, it's always been 65. The mid split was an 85, and that was in the spec for DOCSIS 3.0. DOCSIS 3.1 expanded at the 204. So, and it's part of the spec. So the hardware and the CPE, the customer premise equipment, have to support those frequency ranges and the capacity to fill it up.
Correct.
But let's not kid ourselves in DOCSIS 4.0. We're talking about, we call it the 10G initiative. That's what it's been for the last, 5-6 years?
It's been for a while. That's been talking about 10G.
And it really didn't mean 10 gigahertz. It meant 10 gigabit per second.
Correct.
That's what we're trying to go for. Not 10th generation or whatever you want to, like 4G and 5G, right? It's 10 gigabit per second. But that was downstream. But in reality, we're trying to do DOCSIS 4.0 to increase the upstream. But to increase the upstream, you eat into the downstream spectrum. Hence, you have to do something with the downstream.
Right.
Either overlap it or extend it further to 1.8 gigahertz. Right. It's actually like 1.7912 or something like that.
Gigabit per second in the downstream.
Because gigahertz.
I'm sorry. Yeah, gigahertz. I'm getting screwed up myself. Because what we're talking about is, right now with DOCSIS 3.1, we're able to go up to 204 megahertz for a return path. But with DOCSIS 4.0, we're going to extend 204 to even higher frequencies so we can have a larger return path and have more speed in a return path. To your point, to have that 10 gigabit symmetrical, or well, maybe not 10 gigabit symmetrical, but 10 gigabit speeds. And that's why you're saying we're eating into our downstream.
Yeah, they were looking at saying 10 gig down, 5 gig up.
Right.
Potentially. And that would be more like aggregate speed that this system could provide. Whether you offer a 10 gig service, I don't know if that would be possible. Maybe it's a 5 gig by 2 gig or something. It's still hella cool.
Yes.
That's a lot of speed. I mean, it's a lot of speed that we even said, do people really need 1 gig? And it's not that people don't need it. They might just want it. And,
Right.
you know, so it comes down to marketing too. Like if I can offer that speed, then it helps keep away the competition, saying, well, if they already offer it, what am I going to have? You know, why would I overbuild? You know,
So there is a lot of marketing competition there for, you know, if you have an incumbent in the area and they're offering gigabit speeds, then the cable operator has to be able to market those same speeds to not lose the subscribers on that network.
Yeah, where they have to come up with sticky apps,
right?
You know, something that makes people stay.
So when we talk about, you know, the fact that we have to increase our upstreams, the first technology, so there's two technologies in DOCSIS 4.0. One is FDX, or full duplex DOCSIS. The other one is ESD, or extended spectrum DOCSIS. So full duplex DOCSIS, let's talk about that first, because full duplex DOCSIS does not require cable operators to go to 1.8 gigahertz or even 1.2 gigahertz, right? It really doesn't force us into those really high frequency spectrums that we believe to be challenging, but it does use a different technology that is still a challenging technology, where we don't have diplex filters in our amplifiers. And that's you know, removing diplex filters from our amplifiers, and we have diplex filters in our amplifiers and nodes to allow signals to go both directions. But it separates our upstream from our downstream. These basically a low pass and high pass filter coupled together. So a really important component. We get rid of that component. How do we have signals going in both directions?
Well, we've always had signals going in both directions because we know what frequencies we're transmitting and receiving, right? Mm-hmm. The CMTS and the cable modem control which frequencies are used. But the diplex filter in the amplifiers, you have different gain stages, right? You have a pre and post amp for the downstream, and usually have just maybe one hybrid or a gain stage for the upstream. But inside that active device, you can't afford a runaway oscillation where the signal on the downstream bleeds over to the upstream, because the hybrid itself is not 5 to 42. The hybrid might be 5 to 200, 5 to 300 megahertz. You're buying generic like amplification, and then you're controlling that spectrum with filters.
Right.
External. So the hybrid.
So we're isolating that return path hybrid from the forward, so you don't have the oscillation that you're talking about.
If the downstream bled over to the upstream, it would then bleed back to the downstream and just run away, and then cause a big spike at a certain frequency, sometimes based on what that total path is.
Correct.
So you can have you make your own like crystal oscillator or some type of oscillator where you have like a CW carrier or something like that.
Well, what happens in today's amplifiers sometimes, if we have some improper grounding in the amplifiers, and we call this resonant peaking, and we can see this in full band capture. It's something that we train technicians on how to identify resonant peaking, where you have too much gain in a downstream. And that's basically what's happening. We're getting a little bit of a feedback loop in the RF amplifier that causes the downstream to have a peak in it. So it's a problem, and we know how to identify it, and we know how to fix it when it occurs. So it's a bad thing when it happens. So if we pull out those diplex filters, to your point, that can cause a real problem in the system.
Balance out the gains on the downstream and upstream, and the total isolation and losses.
Correct.
So the losses actually exceed the gain in the total path. There's 3 places where it actually can occur, and it brought up something I remember from Jim Coons. Remember Jim Coons?
Oh, yes.
I think Comcast way back in the day at Minnesota area. I'm sure he'll like to shout out here. I'm not even sure where he's at right now. It could be Thailand or something. But a great guy. And he had a Prezzo when I worked at C-Corp years ago, 20-some years, 25 years or 30 years ago. I don't know what it was.
You're old, John.
And it was a one-way amplifier that you got a kit to upgrade it to 2-way. And the diplex filter, there was no diplex filter because it was one-way. So there was a jumper. And then you got this kit with diplex filters you would plug in, and people forgot to cut the jumper. So the signal could loop through the diplex filter and the jumper right there at the diplex filter location. So there's a little oscillation right there.
Right.
The other one was just what we talked about, downstream and upstream. Maybe someone changed out the hybrid and there's more gain than loss because they had a hybrid upgrade or something.
Correct.
The other one was, what if you have power in and out of the amplifier? The only thing that creates this non-loop between power and, say, your upstream path or even the downstream path would be the RF chokes.
Right.
When you put in an input and output fuse, you create a loop between the gain stage and the power stage. So it could loop that way. And we've seen that occur back in the day. Secor, we had some issues where I think we ended up creating a filter on an input or output fuse. So it created maybe more losses so that signal wasn't bleeding over. It was very low frequencies, like 2 megahertz.
Yeah.
But
so you threw out RF chokes. We should explain those for anyone who may not know. An RF amplifier, you have both AC power and RF coming in to the RF amplifier. The AC power, or quasi-square wave signal, is required to power the RF amplifier. But on the coax cable, we have AC power and RF coming in at the same time. Now, what that RF choke does is it allows the RF to go into the amplifier, and it decouples the AC power off of
Look at the name. Look at it. It chokes the RF.
It chokes it. That's a great way. Yeah, it chokes the power. It chokes the AC because it's a very low frequency.
It chokes the RF.
Yes.
So the RF chokes to choke the RF, so the RF goes the right way. There's a capacitor that would block the AC from feeding the RF side.
Correct.
And then the AC would just go down through the choke and to the AC side.
Yeah.
That way you can just feed your power pack, and then it provides 24-volt DC to the hybrids and all that.
Yeah.
But
so basically, the choke just separates the RF from the AC.
Yeah. It's like a diplex filter for power.
Yes, exactly.
RF, right. And we know the AC is at 60 hertz or 50 hertz in the US or in UK, and it runs right down to the center of that center conductor.
Yep.
Unlike the RF that has a skin effect and it's traveling on the skin of that center conductor. That's why the center conductor of our coax is copper clad aluminum. We're not going to do full copper because it's too expensive. And none of that RF is running down the middle. It's just really AC is running down the middle, or the whole cross-sectional area, or whatever it is.
Right.
But either way, so that's where you get these runaway loops. And we talk about diplex filter, why we have diplex filters. Full duplex DOCSIS, we knew that there was problems going to 204. I have cumulative leakage index, leakage testing at 135.2625 or whatever it is. I have old set-top boxes at 74 megahertz that may be frequency agile to move it to 104 megahertz. But that's MPEG-2 set-top boxes, right? Digital set-top boxes, out-of-band signaling for the set-top box. And you could say, I'll just get rid of it. Well, when you have 2, 3, 4 million boxes out in the field, that's a little hard pill to swallow. So there are things in the downstream, like in the UK, in Germany, they had to carry the FM radio. From 88 to 108, they had
Correct.
to carry that on the downstream. So how do you increase your upstream to 204 if you're reliant on that spectrum for downstream broadcast from the head end?
Correct.
How do you get rid of that signal? Do you move test equipment, sweep equipment, leakage equipment?
These are all challenges that we have to deal with as part of whether it's FDX DOCSIS 4.0 or ESD DOCSIS 4.0. These are some of the challenges in deployment that cable operators will be facing moving forward. So FDX, how does FDX compensate for removing the diplex filters? I think it's the echo cancellation part of it.
Yeah, that was part of the secret sauce. Was
yes.
And let's say echo is reflection, and reflection, right? So if the downstream signal, and I can design it enough, instead of a diplex filter, I could put a directional coupler in as a diplex filter, separate. Directional couplers have a little bit better port-to-port isolation, output-to-output isolation, or input-to-input, whatever you want to call it. It might be 40 dB of isolation, which is great. There are ways to add more isolation so it doesn't bleed over. But a diplex filter is frequency specific.
Correct.
Whereas the other idea, there's no frequency specificity to it.
Which means we can change the frequency that our downstream and our upstream has without having to go in and change the diplex filter now, if we don't have them in our amplifiers.
Yep. So doing that, it helps solve the problem of the internal oscillation, or whatever you want to call it, a
Yep.
peak resonant. But what about downstream signals that are coming out 50, 55, 60 dBmV? Super high outputs now, right?
Very high.
And it's going down to the first tap or splice in the middle of your span and reflects. That reflection could be so high, it's still high enough to bleed back in and cause problems.
Right.
Or re-reflect and affect your downstream original signal.
So you have two downstream signals. You have your original signal and then a reasonably high signal that's been reflected coming down. So now your modem or your set-top box that's trying to receive these signals is going to have multiple signals coming into those devices. So these are what we call micro reflections.
Yeah, just like we always talk about for upstream.
Right.
Now it could be kind of detrimental for downstream as well, and affect the active devices. So they have this thing called echo cancellation that it knows when the original signal goes out, and it knows what that signal would look like in a difference of time.
These reflections that you talk about.
And it can cancel that out digitally. So it's not an RF filter, but digitally it can cancel it out like pre-equalization can do for upstream.
The same way it's the same way pre-equalization does it today when we take advantage of that to identify problems in the plant.
Mm-hmm. So what's interesting about a fiber node is, one, we also know that we're going to go DAA, distributed access architecture. To do a 204 megahertz upstream, we have to digitize the upstream. We're going to have really bad laser clipping. Mm-hmm. So we'll always worry about laser clipping and overload. If we make it digital, we don't have to worry about that anymore because it's an on-off fiber. So we do a DAA node. Now remember, coming into the node, you have upstream and downstream fiber, right? Different wavelengths, or same wavelength but different fiber.
Could have two fibers, or could have one fiber with 1510 and 1310 nanometer optics.
Right? The only diplex filter in a node is on the output. If we do FDX, we get rid of that, put a directional coupler in, so there's no frequency-specific cutoffs and stuff like that. So we have an echo cancellation on the output of the fiber node, and that's enough because there's no real loop in the fiber node. There's no feedback. There's no input diplex filter, right? But when you get to the amplifiers, it's a different story.
You got both. You got input and output on both sides of the amplifier.
That's where things can get a little sketchy. And FDX was a technology that said, we could run frequencies on top of each other if one frequency has a better MER than the other frequency. So this is kind of the key is, let's say I want to transmit at 100 or 300 megahertz on the upstream. And you're far enough away that I would not interfere with you. And your signal, downstream signal, is always on. It's broadcast, right? Like CMTSs are today.
So I'm continuously transmitting at 300 megahertz in the downstream, right? Is that what you're saying?
Yes. So let's say you are receiving downstream at, what do we say?
300 megahertz.
300 megahertz. And that signal is definitely coming to me too, because there's no way to just shut it off.
Always transmitting in the downstream.
Always transmitting. But it's hitting my house at +5.
Right.
I'm transmitting at 48.
The cable modem's transmitting at 48.
Yes.
Also at 300 megahertz?
Yes. Same instant in time, same frequency, but the levels are good enough separation that my MER will be good enough for me to run 1K QAM maybe 512 QAM.
In the upstream.
Maybe 2K QAM. So that's kind of the key is where interference affects each other, and the MER readings will dictate if it'll work or not. So the problem with FDX would be understanding who interferes with who. So they came out with this thing called sounding, where the CMTS would tell the modem to transmit and then monitor all the modems downstream and say, all right, who has a poor MER because this guy was transmitting the upstream? Because
they
even though your
with each other.
Didn't affect me, what if my upstream affects you?
Like your neighbors.
Yes.
Because these two modems could transmit and collide with each other, right?
And they're definitely going to be the same frequency, but if they're the same level, all bets are off, right?
Right.
There's zero MER. Bad MER.
Really bad MER.
So two neighbors will definitely be in the same interference group.
Right.
They will never be full duplex. A modem will never be full duplex. I can do upstream or downstream. I can't do both at the same time.
Yep.
If you're my neighbor, we both could maybe share the upstream at the same time and do the downstream at the same time, but we can't do upstream and downstream at the same time.
We gotta be simplex.
It's simplex. Some people said half duplex. I'm like, half and do. Can't figure it out.
Have to.
Simplex. It's simplex. So basically, a tap will be simplex. An amplifier leg would be simplex. When you run the sounding and interference groups and transmission groups, you're going to find that you might end up, because one of the almost requirements was node plus 0 for FDX, which was a non-starter for a lot of people.
The original requirements.
Node plus 5 amps, node plus 6 amps. I don't want to change my spacing. I don't want to change my tap locations, my amplifier locations, number of amplifiers, my power supplies. I don't want to change any of that. If I'm going to upgrade, I want to make one visit and maybe change out a module in the housing and be done. No checking the connectors or changing anything. So there's some requirements or prerequisites that these companies want, and that's not to spend too much money, obviously, and keep using what we have. So the FDX, I think, if we're going to do an N plus 2, N plus 3, there's some people touting amplifiers with echo cancellation. I believe when we look at it, we're going to find that any leg that has a bunch of amplifiers is going to be one big interference group. So it's not going to be FDX. The only place it'll be FDX would be this leg of the node against this leg of the node. Two different legs of a node. They would probably be, full duplex.
Wouldn't it? Like the core of the network would also be more like full duplex as well.
So it kind of begs the question is how there were some studies done saying how often do we really need the downstream and upstream to be on at the same instant in time? Same exact instant in time. And someone came up with it was 14 seconds a day, or it was something like ridiculously low. We definitely need the speed, but do we need it at the same instant in time? And before I go down that path, let's look at what the other solution was, the other camp versus the FDX, and that was ESD, Extended Spectrum DOCSIS. Why don't we just keep doing what we're doing? We do diplex filters, we do splits. Let's just move it up. If we move the upstream up to get more upstream speed, we get into the downstream. How do we get more speed out of the downstream? Reclamation of digital QAMs. Get rid of it all. Do all DOCSIS 3.1, some single carrier QAMs for the old legacy modems, but get rid of the set-top boxes, do all IP. IP set-top boxes, all IP. Other option is go from 1 gig to 1.2, which is part of 3.1 spec, all the way to 1.8, which is the 4.0 spec. It's actually a 1.7.
Yeah, and that's extended spectrum DOCSIS. So there's FDX, which really doesn't go above a gig. Extended spectrum DOCSIS goes to at least 1.2 or 1.8 gig. And we saw that at Expo, where there was a lot of 1.8 gig equipment. I mean, so this stuff is real. And I just want to, in the chat room, Rick Busey asks, he says, is this a VHS or Betamax thing where, there's kind of two technologies of FDX and ESD, Extended Spectrum DOCSIS. He says, I'm sure this will be supported, but do you think that they will have more? What will have the most adopters? And as he says, right now Comcast seems to be betting on FDX, where most other operators are looking at ESD. So
I use that terminology all the time, and I would say a better analogy for the Betamax versus VHS would be Remote PHY versus Remote MAC-PHY. That is much better because Remote PHY came out first. It got adopted quicker. It got interoperability quicker, and people are solidifying on Remote PHY.
Yes.
Even though Remote MAC-PHY has some good, legitimate reasons why it works, and that could be distance and timing and stuff like that. But we found ways around that for Remote PHY. And Remote PHY mostly is like changing out an existing node area that's only 20 kilometers away.
Yes.
So Remote PHY works fine. But if you want to go 1,000 miles away, you could do it with Remote PHY, but it's probably even easier with maybe Remote MAC-PHY.
Right.
Or Remote CMTS or something like that. In regards to FDX and ESD, I don't think it's a either or. I think it's going to be both.
Right.
I think you're going to find that you have, say, I'm Charter. And I'm like, you know what? I have a system in St. Louis. It's very densely populated. Node plus 0 makes sense. I can hit everybody with a node.
Right.
I don't need a bunch of amplifiers. but I'm out where I live right now. No plus 10 could be the norm.
in a rural area, yes, it makes no sense. You gotta have amplifiers in rural areas.
So it's either that or wait for Elon Musk to come in with Starlink.
But Rick goes on to says I think the amplifiers for FDX are more complicated than ESD than expected. So there are amplifiers for FDX, but the complexity and complexity drives cost as well. So that's going to make it maybe an issue there as well. And he says the reason for FDX seems to be more of a marketing checkbox, symmetrical service. So I think is that true? Do you think?
I think it's a way to offer the higher speed, to ring the bell for the customers to get a higher speed without having to go to 1.8 gigahertz, without changing any taps. That might be a big one right there, right? Changing out all your taps, worrying about the coax and connectors going out to 1.8 gigahertz, not having to change your set-top boxes. That's a big one, right?
Yep.
So your bean counters are looking at how much money you're going to need to change out all these set-top boxes, your CLI, your test equipment, and that could be one of the bigger drivers for, say, Comcast or a big company like that, betting on FDX. They don't want to make that investment to do an ESD, but they're going to make the investment on FDX so they can save on this part.
Yes.
And put money in this part.
Regardless of which technology you go with, FDX or ESD, as JazzCat 102 says, you have to go all IP in your network because it's really, if not impossible, it's very difficult to send analog signals over either an FDX or an ESD network because they're really meant to be IP based. So that is something that operators have to do.
Let's take a step back from that because remember, our digital signals are still RF, QAMs, quadrilateral amplitude modulated. It's still an RF signal. It's not real digital IP on-off light, right?
Yep.
So I can still do MPEG-2, QAM, analog video, if you want to call it digital. Let's call it digital video. Yeah. Digital video. And that could be conserved in an FDX or ESD solution.
Correct.
Right? It's when you go EPON and GPON that you have to be a pure IP solution. And I brought up earlier, you have to do IP video if you want to reclaim those digital QAMs for more spectrum space to do more 3.1.
Mm-hmm.
But if you do FDX or ESD, you can still do those digital QAMs.
Correct. You just can't do any analog. You can't do anything.
Correct. Yeah. The old 6 megahertz, video, chroma,
those are
audio,
gone.
Those are gone.
Yeah. And there's still a number of operators out there that still have those analog channels. So they have to migrate away from those and get into a digital network, if not IP network.
You would think if the off-air broadcasters went digital years ago, why are we still? But then again, that might be the sticky app, right?
Yep.
That's the thing you offer that keeps grandma still paying for her service because she has an old TV. She might have a new TV, but she has 2 other old TVs that only get the video.
Yeah. So we said with FDX, challenges were the echo cancellation and feedback and amplifiers and things like that. With ESD, challenges are going to higher frequencies are, that's alone is no simple task going to 1.8 gigahertz.
Correct.
We've not done that before.
Yeah, we worry about, as an RF guy, I know that cable and the plant gets very more particular.
Yeah. Is very more, is that proper grammar, John?
Sensitive.
Sorry, Mia's laughing over here, so I had to...
It's persnickety.
Yeah.
My cable gets persnickety. When you get higher frequencies, any little ding in the cable, craftsmanship, it really shows up bad.
Very more bad.
Yeah, very more bad. Very more better.
Yeah. That's as bad as it gets, man.
We're on Penn State on right here, so that's why
we both went to Penn State. Yeah, that's why we speak this way. We learned a lot there, man.
Yeah. So we definitely are worried that craftsmanship of the connectors, the heat shrink, the RF connectors, the seizure screws, the modules, the housing, putting tap housings side by side could have a detrimental effect you never thought about because of the cavity of the housing itself bounces back and forth.
Yep.
And if you put another one right beside it, housing to housing connector, that could back and forth, back and forth, back and forth, back and forth. You don't know how things can build up. That actually happened to me in Japan, and no one really thought, an 8-port tap would be right next to another 8-port tap, next to another 8-port tap. So you end up with the size of the tap housing having a cavity affecting the next one and the next one and adding up and causing a frequency runaway oscillation.
Yeah.
Or suck outs or something like that, like bad grounding.
Well, for any technicians who's worked in the field and spent time in the higher frequency range, they know how sensitive it is to things like loose connectors or water that gets into an amplifier or passive dramatically attenuates high frequencies. It's very, very sensitive. And that's in plants that go to a gigahertz. Now we're going to be going to 1.8 gigahertz. We're almost doubling the downstream, doubling the frequency, so 1 gigahertz to 800 more megahertz of frequency that we're looking to add on to the plant in extended spectrum DOCSIS ESD. So I think that is a huge challenge that we're going to run, the newer challenges that we're going to run into solving issues that we've not experienced before. I think those are going to be lovely.
Another problem with ESD, let's say, I'm happy with my downstream. Yes, I'm going to upgrade to 1.8, but I don't plan on activating anything past 1.2 for a while. Maybe that's the case. But you're going to extend the upstream to get the upstream speed. That's why we're doing this.
Yes.
So let's say that you're going to go to 396. The diplex filter no man's land is about 25%. They're trying to get that down to 20%, but it's about 25% of your highest upstream frequency. So if you go to close to 400, 25% is 100 meg. So your downstream doesn't start till 600.
And what you're talking about, this no man's land, you're talking about the gap between the low pass and the high pass cutoff in the diplex filter. So right now, like in a 42 megahertz return, that gap is between 42 megahertz and about 52 megahertz. So you have that gap. And you're saying as you go higher in frequency, that gap is going to get wider and wider and wider, that you just can't do anything with that frequency range.
Correct.
In basically the cutoff between your diplex filter.
Yeah. So if, the highest frequency listed for DOCSIS 4.0 is 680, 690, 680.
I thought it was 695, but I could be wrong on that. Definitely have it written down.
It's like add 96 to 204, that gets you 300. Yep. It's 396, add 96 again and again and again, and that gets you to 6 something, right? That's the highest it's listed. So in FDX, 108 to 684, I think it is. I think it might be 684.
You're right. It's 684 in a downstream.
Spectrum is allocated for upstream and downstream overlap.
Yep.
That's the spectrum for the overlap. That overlap could never be a primary downstream either, by the way. The primary downstream where the modem locks has to be outside that overlap.
So meaning it has to be higher than the overlap because it has to be in the usable channel range.
Yeah. So it'd have to be above 684 somewhere, like your PLC or whatever you're using for as a primary channel. Could still be a single carrier QAM, but it's got to be way up there now. So that's the talk about FDX is overlapping 108 to 684. But for the upstream, what were we getting at? If I extend it out and I use ESD, the diplex filter can be huge. If I go to 684, 1/4 of 684 is probably over 150 megahertz of no man's land in my diplex filter.
It's a lot of lost bandwidth.
We're at almost 700. 150 above that, it's like 850. Yeah. Man, you just lost all your downstream, so you have to go up to 1.8 gigahertz.
Yep. Yeah, because imagine if we had 150 megahertz of bandwidth we could just allocate to the upstream, and you're just saying we're going to throw that away. So it means we need that much more downstream spectrum. So it's really pushing us to higher frequencies.
Yeah. That's why some people are thinking if I do go past 204, maybe 396 is the next split I do. And it lasts me for the next 5-6 years, and I retire.
Or we go fiber.
After that,
we go to fiber. Would be the next thing.
And then really, that's the end goal. I think is fiber.
Now
we all say that.
Now we've talked before about 85 megahertz, 204 megahertz, the challenges that we're going to have in the upstream with attenuation, thermal changes, and things like that. And do you see or do you know if vendors are going to put automatic gain control or anything like that in the return for our amplifiers, or are we just going to have to build headroom in for our amplifiers for the return path when temperature changes and we have that excessive attenuation due to cable loss and things like that in our returns?
So 204, I think we can make it no problem if we design properly and we allocate some headroom. The modems, 3.1 modems have more power than 3.0 modems, apples to apples comparison. So putting a 3.1 modem in gets you some headroom. Throwing in DAA and distributed access architecture, you're putting the CMTS right at the node now. So instead of having to hit the node at plus 10, maybe you're hitting it plus 3.
Right.
Because normally you want to hit the CMTS front end at 0. So you just gained a little bit by going DAA because you don't have to hit the node with such high levels anymore because it's right there. The upstream chipset is in the node. So you got higher powered modems, lower required input at the node. So that helps right there. But with temperature past 204, I ran some numbers on that before, and I'm like, it could be a +8, -8, +10, -10 swing. Remember, if it's black jacketed, sun loaded cable, it's like 40 degrees above ambient temperature because they're sun loading. And then you go drop cable, span, node. It's got to overcome all that. So you can't rely on this long loop level control of CMTS and cable modem negotiating levels to make up for a 20 dB swing, 10 up, 10 down. You might have 3 dB of headroom. So upstream AGC or ALC, I used to call AGC was a pad change and ALC was a slope change. Mm-hmm. Whatever you want to call it, automatic slope control, automatic level control. It's going to be needed. And there are all the manufacturers, ATX, Technetics, anyone making amplifiers. AOI is now jumping in the game as well. They're all looking at smart amplifiers and
that's the big talk. Yes.
Yeah, looking at the downstream AGC circuitry and extrapolating that information for the upstream. And it does make sense because remember, if your amplifier's here, you are checking levels coming in on the input cable. And if levels change, temperature is affecting that cable and you adjust the AGC so you have constant output of the amplifier.
Correct.
Well, that cable is the same cable this upstream has to compensate going back. So if the downstream knows what this cable is doing, the downstream can dictate or extrapolate for what this upstream needs to do to overcome what we think is going to happen. So we hit the next amplifier flat.
So with the smart amplifiers, and we really haven't talked about smart amps before, they will have the ability to allow cable operators to automatically configure the downstream padding and equalization, configure the upstream padding and equalization, and this will be done remotely. We'll have a way to communicate with the amplifiers remotely, so we can make this change. Do you see that as we go to ESD, where we have a 384 megahertz return, will we be able to potentially have a quasi real-time ability to adjust the return path in smart amplifiers to compensate for changing returns? Is that something that perhaps would be valuable for us in an ESD DOCSIS world?
Yeah. It's kind of 2 or 3-fold. One is if I don't have to have every technician running around with a tackle box full of all these pads in 1 dB increments, I could probably save thousands and thousands of dollars, wasted dollars, and in stock dollars just sitting there because I got rid of all those accessories. So the accessories are gone. I don't need them. I don't have to worry about them. I don't have to worry about human error. And then I don't have to worry about changing things on the fly or making truck rolls. If I can see my amplifiers, I have visibility and I can change things on the fly, or it just automatically says, this is a level, this is a tilt I want, keep everything constant. So I think that's the way to go. But it was always, I think technology is finally catching up where we have the smarts on smaller chipsets and we can do this at a cheaper price. But you mentioned about cost, but it's also power too, right? The more devices you put in that eat power, the more I have to worry about the total wattage of the device. There's some limitations there as well.
Yeah, and that's the struggle with smart amplifiers. There's a lot of benefit that we can get from smart amplifiers, but then there's the trade-off of cost, reliability when you're adding more tech into the smart amplifier, and then power. So I'm really interested in the smart amplifier technology, but I'm also really, I guess, kind of cautious to see how they get rolled out and how they work over time. It's kind of that opportunity cost trade-off that we're looking at with those technologies.
And I mean, I have I always have comments, but
Yeah, of course.
the one
And
thing
subparts to your comments.
probably subpart A, B, and C. So the communication is kind of interesting, and this is why I agreed to consult with Technetics. I think they're doing some cool stuff. One of the things, and it's the terminology, it's in the industry, but we don't use it very often, is PLC, and it's not the physical link channel or whatever. It's power line communication. So you can look up power line communication. But in my mind, that sounds like communication over a power line. And that's not what they're talking about. It's using the power line in the coax, which we call the center conductor.
And we talked about earlier.
Communicating through that center conductor at a real low frequency of like 400 kilohertz.
Yeah.
It's not RF.
Very effective way.
It is RF, but it's really, really low frequency RF. And because of the skin effect, it wouldn't be on the skin. It would be more like going down the center of the center conductor, like our power does. And because it's low frequency, it wouldn't get cut off by the RF choke. It would go through the RF choke through the power line of your amplifier. So even if your amplifier is dead and there's no power to it, you can still communicate to the next amplifier or the next one. You know what I'm saying? So it's kind of a cool idea because I can almost have an out of band communication, out of channel, out of, I don't know what you want to call it, out of this world.
Yeah. Well, I think it's out of band. I think that, I mean, it's still because it's not within the main channels. And the reason that vendors are looking at doing this, because some people say, why don't you just put a cable modem in there and use a cable modem as your communications? Cable modems draw a lot of power. So we're looking at alternative ways, alternative communication ways to communicate with the amps that are cost effective and use very low power. And this power line method it's a brilliant idea. So
and they need RF.
Yes.
What if
exactly.
RF goes down?
Or what if the DOCSIS network is down and we still need to troubleshoot and get data from the amplifier to see?
My amplifier down. Oh, I can't get to my amplifier because it's SNMP or it's DOCSIS related and it's down.
You can't troubleshoot if the DOCSIS network is down, so you lose that visibility. So this is an alternative, like you said, out-of-band method to be able to get the telemetry data from that smart amplifier to see why your DOCSIS network is down, and that I think is brilliant.
So that goes hand in hand with the smart amps and the upstream AGC and the leveling control and temperature effects. New mimics, new hybrids are lower power, more powerful. One of the things we were worried about with 1.8 is higher frequency, more loss in the coax. Am I going to just go out and start underspacing my amplifiers because I can't reach? Yeah. So now I got to cut cable.
I was going to say,
cut cable, you might as well run fiber.
Yeah, that's not going to be very cost effective.
Yeah. So good thing technology is giving us higher outputs, maybe less power draw, and we can upgrade housings without having to respace.
Yes.
Which is, I think, it's a number one rule. If I can do taps without respacing and cutting them out, if I can do amplifiers without respacing or cutting them out, that's, I think, a no-brainer. If I can put in a module that a technician doesn't really have to think too much, they just plug it in and things kind of set up on their own, that's going to be worth its weight in gold as well. And it also brings in the time to market. Like some of the sessions we were at during SCT Expo a couple weeks ago, it talked about the labor market. And it's going to be hard to get people to actually upgrade an entire plant if it's going to take them, a lot of time to like mess with connectors and you know how it is.
Massive amounts of work. Yeah. And so I think that brings us to an important question. I mean, John, if you owned a cable plant and you have DOCSIS 3.1 already deployed, when would you be looking to upgrade to DOCSIS 4.0? And if so, would it be FDX or ESD?
So I would cherry pick, I think, what I need. And here's why I said everything is going to be together or you're going to do both. Or if I had a system that was very densely populated, I might do FDX because I could do N+0. And I think the N+0 gets me a lot closer to being able to do something like that.
But it has to be really dense.
Yeah. If the CPE on the market will support both FDX and ESD, that'll be perfect.
Yes.
But if I have to pick one or the other, I'm probably going to go the ESD route because I think it'd be less complex, less complexity. And it might even be cheaper modems as well. So there's this third option we're all looking at. It's called Unified DOCSIS 4.0. And I think Broadcom might have the even a trademark name on unified. So we call it United, or I don't care what you
Unity.
call it. Yeah, Unity. So, and the idea, and I had this, I looked up some of my old slides from like 2-3 years ago, and I came up with my own acronym.
Of course
it's
you
truly
did.
an acronym. It's called FUD. And FUD to us is fear and uncertainty and doubt, right?
Yeah.
But I called it, and some people already called it something else, and I didn't like the name. They call it static FDX. I called it flexible upstream downstream.
Right.
And that basically meant there's no diplex filter in the amplifier, so like FDX,
Okay.
but there is no overlapping frequencies at all. So it's not full duplex.
So you don't need
But
the
you're
echo
not.
cancellation then? Is that
You'll still need the echo cancellation because you don't have diplex filters. You don't
Okay.
want things leaking around.
right?
But you allow the CMTS. The CMTS is going to have to be smarter too, because remember the downstream's always on. The CMTS or cloud native CMTS or whatever's driving the signal or telling the RPD, the remote PHY device, to turn on. It's going to have to turn on and off. So what we're saying is, say I want 10 gig, the CMTS sees that and says, oh, I'm going to schedule downstream from 108 to 1.2 gigahertz, all OFDM, 6 blocks, and you can do all 6 blocks.
Okay.
So I can ring the bell, 10 gig. And then you're like, oh, I need 2 gig on the upstream. CMTS is going to say, all right, turn off these downstreams in the 108 to 684, turn on upstreams, and let you transmit from 5 to 684 megahertz OFDMA. So it's one or the other. It's not at the same time, but that means the CMTS has to be smart enough to turn downstream on and off. It doesn't do that today, right?
Correct.
You hard set it and it's done.
So, I mean, if you're doing that on and off, are you able to maintain streaming services like voice and video? Because typically today, when you have say we're watching Netflix, you have that continuous streaming. What happens when you shut it down?
You would make sure multicast and voice and all those services are above 684 on the blocks.
Okay.
They're scheduled on the blocks above 684. The other blocks that could go up and down, that would be like some
lower frequency blocks.
Yeah, the frequency blocks. Yeah, below 684.
Right.
Those would be the ones that maybe you say that's like the bleed over when someone wants to get 10 gig. Well, they're always using this spectrum first. And then if they want to ring the bell and they really need it, we'll activate these and they'll start bleeding over into these other OFDM blocks.
So it's very frequency agile then, that you can have some parts that are going to be continuously streaming, and then the lower frequencies you're going to have kind of on and off downstream.
Yeah,
right. I mean, it starts to make sense.
Yeah.
It seems to be a little bit more flexible architecture. Flexible of an architecture.
Yeah, flexible. I call it flexible upstream downstream FUD.
Yeah.
It's just
FUD. I like the F.
But the idea is you could. Oh, we're getting time. I didn't. Is Mia now running one of those little sound things?
Shit.
But you could say, I need to hit certain speeds, but I don't need to go to 1.8 gigahertz.
Right.
Maybe I just go to 1.2, and when I need it, I could. If I need the upstream,
you can scale up and scale down as needed.
Yes.
So rather than splitting the node, you just increase your frequencies to a higher frequency.
So I like that. It's almost like the best of both worlds, but I think the complexity is going to be in the CMTS being able to schedule the downstream to turn on and off. Because right now you configure a downstream controller, and QAM mod and profile modulation, and then you say, all right, turn it on, and it's on.
Yeah.
That's it. Upstream's the only thing that gets scheduled.
I'm sure the spec writers at Cable Labs love our discussions, John.
So, I mean, I think that would be the way to go, because I'm not hamstringing myself, pigeonholing myself, whatever the word is.
Yeah.
And going
Putting yourself into a corner.
Yes. Any metaphor or saying you want to come with, I'll go with that. Because then they're always Broadcom. I think Max Linear is getting into the game as well, which is great. They're making chipsets. So if they can provide me a CP, customer premise equipment, that maybe has echo cancellation, but can do a flexible upstream, downstream, has all the capacity in the modem to do 10 gig down and 5 gig up, then I'm kind of future-proofed. There's no diplex filter in it. It's like if it was ESD, there would be some type of programmable diplex filter. And maybe there would be a diplex filter that's programmable, But then remember we just talked about that frequency split thing, and
Yeah, the higher you go, the more bandwidth we waste. So
yeah,
I think Broadcom and Max Linear know exactly what your Christmas wish is now, John.
yeah.
So hopefully they'll get working on it and have that delivered by January.
December 25th.
Or before.
Yeah, yeah.
So, all right,
there are some 4.0 modems being tested right now, but I don't know if they're one or the other.
Yep.
FDX versus ESD.
So if you're a cable operator, I'd love to know what you plan on doing. Drop it in the chat. Drop it in the chat room. Let us know. Are you going ESD? Are you going to go DOCSIS 4.0 ESD? Or are you just going to stay at DOCSIS 3.1? Or are you going to go all fiber? I think there's lots of options, which that's a great thing to have options. And options to extend DOCSIS, preserve your coax, or options to go all fiber. Love to know what you're going to do. Let us know.
So that came up during the one session I attended, and the all fiber, I think, makes sense when you cherry pick a business subscriber.
Yes.
That they're willing to pay more money, and you cherry pick them, throw them a high speed fiber connection. What's great also is you offloaded them from your existing network, which frees up capacity for everybody else, right? Because they're the heavy user.
Correct.
So keeping a heavy user on your shared network can sometimes be more detrimental. Maybe taking them off and putting them on. The problem with all fiber, and we brought this up, was it has to be all IP.
Yes.
Once you go EPON, GPON, there can't be any video there. And if you say, we'll do RFOG, that has its own problems. You can't do really OFDMA efficiently with DOCSIS 3, OFDMA with RFOG. We've talked about that before.
Yeah, and I think, a number of discussions we had was at SCTE Cable Expo with some different operators was around the cost of going all fiber. Because a number of our viewers are like, why aren't we all fiber right now? The cost to go all fiber will put operators out of business. It's very, very, very expensive. So a lot of operators that have, kind of said, hey, we're going all fiber, they've pulled back on that because they saw the expense that it has. So, they're the plans. We're still eventually going to be fiber everywhere, but it's just delayed because it's very expensive to push fiber.
I can see it. I can see the industry going to 4.0 in some capacity, one or the other capacity, and then fiber even deeper, and still finding the numbers are cheaper to do maybe remote PHY to a tap.
Yes.
And still have the coax or Wi-Fi or FWA or something, fixed wireless or something from the tap into the house. And the house should be a gateway, right? No more coax in the house. It's Ethernet, Wi-Fi 7, whatever in the house. So there's no RF problems in the house. And then from the tap, maybe you have 8 customers off of one RFI device. So you got fiber really deep, inexpensive. How that you're going to power it up might be a different story. You're running fiber all the way to the tap. Maybe it's backfed somehow. So I think you'll find that the cost, even running fiber to the curb or the next to the house, is still cheaper than fiber right into the house.
Yep.
Absolutely. You know what I'm saying? Because, the trenching, the right-of-ways, the timing, delivery, the end devices.
It's the final 100 feet that's very expensive. There's lots and lots of studies that talk about that. We'll take a couple more questions in the chat here, and then we're going to wrap this up. So Abraham talks about, he says, as a customer, he's talking about, I hope the market more on the reduction of latency. So he's talking about really low latency, or at least consistent latency in DOCSIS 4.0 than multi-gigabit speed. So he's more interested in the latencies, maybe a gamer or something like that. As most consumer hardware don't support multi-gig speeds. So there, I think there's multiple issues on that comment, Abraham. So thanks for the comment there. We are like low latency, or at least consistent latency is something that as an industry we're focused on. And the newer hardware, a number of DOCSIS 3.1 modems are supporting like 5 gigabit per second ports on the back, and the DOCSIS 4.0 modems that will be coming out will all, I think, support at least 2.5 or 5 gigabit ports on the back, if not more. That's just common in the hardware now.
25 gig ports.
I'm sorry, what was that?
Potentially a 25 gig port.
Yep.
Because if I'm trying to offer 10 gig service, you'll never get it from a 10 gig port. So to hit
Correct.
10 gig to ring that bell, you might need a 25 gig port, or, and we talk about, multiple. One device doesn't need 1, 2, 3 gig, but your house is its own little network microcosm, and you might need 5 gig in the house because
Correct.
you have 10 different devices.
Multiple
So,
people using
yeah.
upwards of
So
a
that
gig.
one modem has to support that 5 gig,
Right.
but it's not for one service flow. It's 10. It's your kid doing one thing, you're doing one thing, and you're DVRing something, and you have a camera and whatever. So there's a lot of things going on at the same time. But I thought what you said about not just reduced latency, but consistent latency. Changing latency really would be jitter.
Yes.
Jitter is more of a problem. If everyone had the same latency, everyone would be happy.
You wouldn't notice unless it's extraordinarily high, like 150 or 200 milliseconds of latency.
Yeah.
But I think so. Rick Uzi asks a question, which I think ties into Abraham's question: will an upgrade to FDX or ESD DOCSIS 4.0 provide any benefits for a subscriber with a DOCSIS 3.1 modem? So I think it's kind of like when we upgraded from DOCSIS 3.0 to DOCSIS 3.1, you relieved the overutilization for the DOCSIS 3.0 users because you're taking subscribers off of the SC-QAM and putting them onto OFDM channels. So now you have more capacity freed up on DOCSIS 3.0 channels. So yes, DOCSIS 3.1 definitely improved the quality of experience for DOCSIS 3.0 users. And I think we'll see the same thing as we upgrade to DOCSIS 4.0. We're increasing the bandwidth on the upstream and increasing the bandwidth on the downstream. So we have now more capacity even for DOCSIS 3.1 users. So it should increase the quality of experience, provided we do everything right when we deploy these networks.
Yeah, at first I was going to say no, but you brought up the good point of like you're sharing capacity.
It's a shared network. So if you give
4.0 and you change out all your equipment, the big advantage is you're adding more capacity.
We make a bigger pipe.
Everybody.
Yeah. If we give it a bigger pipe. So,
yep.
And Abraham says, yes, the modem ports may have multi-gigabit speeds, but not my network switches or my Wi-Fi or my laptop over Ethernet. So, ideally you have a bigger pipe coming in, Abraham. But you make a very good point, Abraham. Your home network, and I think this goes for all home subscribers. If you have issues in your home network, fixing DOCSIS or giving a bigger pipe into your home network isn't going to fix your problems. You got to make sure your home network, your Wi-Fi network, your internal switches, everything like that is operating well. Because there's a lot of times we see this as operators that the DOCSIS network is working fine, but there can be in-home Wi-Fi issues that are a problem. And so we got to, a lot of times we're fixing subscribers' networks in order to resolve the quality of experience for subscribers. And there was no issue on the DOCSIS network. Now, there's lots of issues on the DOCSIS network that we have to fix too. But many times technicians are trying to fix in-home issues for subscribers to resolve individual subscriber issues. So good point on that, Abraham.
And isn't the consortium that works on Wi-Fi working on 7 now? Wi-Fi 7?
Yeah, at least Wi-Fi 7, yeah.
Yeah.
So, and those are like gigabit or higher speeds that we can get on those networks.
Every time we go with new technology, the Wi-Fi consortium gets together to try to keep up with it.
Yep.
So, but you could have CPE that still has, older Wi-Fi that will never get past 1 gig.
Or a subscriber that has just one access point in their home and their computers or their laptop or whatever is far away from that access point, and that's going to have them really low speeds. So making sure you have a good Wi-Fi network in your home is really important. Having good speeds, low latency, all the things that you want for good quality of service. And I think with that, John, we've wrapped up another episode. So
yeah, we covered a lot, right?
We did. We covered a lot more in DOCSIS 4.0 in this one. So a big thanks, John. We really appreciate the knowledge you dropped on us again today. And thanks to our audience. Thanks for the questions. Thanks for tuning in. We wouldn't be able to do this without you. Catch the amazing Ron Rannick next week, November 10th. Ron will be telling us about what is RF. Can't wait, because that will also be some great information. So, John, thanks again. We'll see you soon. Our next episode. So,
all right.
See you all. We're out. Have a good weekend. Bye all.